is 3.2.1 and focuses on asynchronous counters in terms of a small-scale integration. Specifically in this lesson, we're going to define asynchronous counters and define the term states and modulus, as well as provide multiple examples of asynchronous counters that are designed with D as well as JK flip-flops. We're also going to explain how an asynchronous counter's ripple effect works, and we're going to summarize the asynchronous counter design steps. So first, let's take a look at what an asynchronous counter is. Only the first flip-flop in an asynchronous counter situation is clocked by an external clock. All the subsequent flip-flops are clocked by the output of the preceding flip-flop. Asynchronous counters are slower than synchronous counters, which we'll discuss later, because of the delay in the transmission of the pulses from flip-flop to flip-flop. Asynchronous counters are also called ripple counters because of the way the clock pulses or ripples its way through the flip-flops. So the number of flip-flops determines the count limit or the number of states. So for example, if we have 2 flip-flops, that means that we have 2 states. So the number of states used is called the modulus. For example, a modulus 12 counter, or mod 12, would count from 0 to 11 and would require 4 flip-flops. So that means 24 equals 16 states. We have 12 that are used. So what we're looking at here is we are looking at an asynchronous counter. So this is a 1-bit D flip-flop with a positive edge trigger. I know it's a mouthful, especially this early in the morning, but what we're looking at is we have a D flip-flop inserted into this circuit over here, and it has a positive edge trigger. What that means is as we go through this timing diagram, we'll hit a clock signal, and then it goes up and counts to 1, and then returns to 0 once we have another rising edge. So that's just going to continue to repeat. Okay, so that's a positive edge trigger for the D flip-flop. So this is the 2-bit up counter, which is the D flip-flops with the positive edge trigger. So with the 2-bit, okay, since we want Q1 to toggle on the falling edge of Q0, we have to clock the second flip-flop from the first. So what that means is that we have to use Q0 to go into our clock for our second flip-flop. What this means is that when we hit a rising edge right here on our clock, okay, we're going to have Q1 obviously change, and then Q0 is also going to change. When we hit that rising edge again, or when we hit when we hit this rising edge, we get the change at Q0. This one does not change, and that cycle just keeps repeating for us to get to our different states. Then we have the ripple effect, okay? As the clock input ripples from the first flip-flop to the last, the propagation delays from the flip-flop accumulate. That means it gets slower with every flip-flop that we add, okay? This causes the Q outputs to change at different times, resulting in the counter briefly producing incorrect counts. For example, as a 3-bit ripple counter counts from 7 to 0, it's going to briefly output the count 6 and 4. So you're going to have flashes of incorrect values input in there. Alright, so now this is a 3-bit down counter with D flip-flops, and that has a positive edge trigger. Okay, so in this case, you need to note that the clocks are connected to the Q from the previous flip-flop, just like we've been setting it up. So if you look at this timing diagram, the blue arrows are indicating when we have changes at different inputs. This is caused by us clocking from the previous flip-flop. This is a 3-bit up counter, and in this case we're using a JK flip-flop with a negative edge trigger. So the active low clocks are connected to the Q of the previous flip-flop, so this is a little bit different. If you look, our clock is actually connected to the Qs and not the Q naughts when we use a negative edge trigger on the JK flip-flops. And then here we have the negative edge trigger with a JK flip-flop with a 3 down. So again, we have the active lows. They're actually connected to the Q naught of the previous flip-flop. So here we have this going to the Q naught. Same thing here. And then we have our modulus asynchronous counter. So this is the 3-bit mod 6, so this is a 0 to 5 up counter using a D flip-flop. Okay, the upper limit of the count is 5, so therefore the reset circuit has to detect a 6. So basically what that's saying is that this is going to count 0, 1, 2, 3, 4, 5, After 5, the circuit is actually going to say 6, like in its circuit brain, but it's going to trigger back to 0 because that 6 is actually kind of what resets everything. So when we go to design asynchronous counters, we have a couple of steps that we need to follow. First, we have to select our counter type. Are we counting up or are we counting down? And does it need to be modulus? Then we have to select our flip-flop. Are we using a D flip-flop or a JK? Then we have to determine the number of flip-flops, okay? So again, we need to make sure that they have that ratio between flip-flops and modulus. And then we have to make sure that we design count our limit logic. So we have to input a reset logic circuit so that way it counts the +1 for the counters and it resets itself.